But picture yourself writing something very simple, maybe an application like this. You have some friends and you want to be alerted when they're nearby for whatever reason. Some sort of end goal, a very simple application, alerts you when somebody's there, has some friends list, maybe gives you a button to say hello. Well, if you're writing this for Android, you're going to need something like this at some point in the code. And this is a giant piece of code that really just gets the location, gets GPS from the sensors on the Android device. You can see we have a bunch of things going on here, a lot of location managers, criteria, contexts, there's a bunch of Android-specific APIs being leveraged to accomplish this task. Also, that at the end, we can return location, which is just the latitude and longitude in a string. Well, like the good mobile developer that you are, you're going to want to send this to other platforms. You want to use all of the other operating systems and different types of devices, ranging from tablets and iPads and iPhones all the way up to Windows Phone. You're going to want to make this heterogeneous. So if you're doing this on iOS, you would probably have to write something like this in Swift, which accomplishes the same thing. Gets the location and uses a bunch of Swift-specific APIs, things like CL Location Manager, and you can see that at the end of the day, it still does the same thing. Returns this string of latitude and longitude. These code blocks are very different, but at the same time have a lot of similarities. You can see 2 platforms is twice the work. You didn't gain anything from the Android code in order to write the iOS side. You didn't really learn anything about the Swift native APIs. You didn't learn anything that would help you accomplish this task. As you might infer, 3 platforms is 3 times the work, and guess what? N platforms is N times the work. Well, what if it didn't have to be that? What if we could actually gain something from that Android experience on the Swift side? Well, that's what we're here to talk about. I'm glad you guys found your way into the right talk. We're going to be talking about natively implementing this component so that we can generate the code from web-based resources to help us synthesize as much of the iOS code snippet as possible. Quick overview of what we're going to be talking about, enabling insights. Just a brief background, since all of you have already read the paper, you're very well versed in what's going on. So we're just going to go through that kind of quickly. Approach, evaluation, future works, and conclusion. So there's three main insights that we're kind of leveraging here. Shared core functionality, which is the kind of big one that we're relying on. Reliance on web-based programming resources and on the web in general, and this notion of accidental complexity. So you guys can see there's a lot of similarity between iOS and Android, specifically Google Maps and Apple Maps. That's a big one. Everybody uses those for GPS at all times. Online tools. Think about this for a minute and see how scary this sounds to you. What if you could not go on Google to look up a piece of code? You couldn't go to StackOverflow. You weren't able to go to Stack Exchange for all the LaTeX documents that you needed to write. Nothing would ever get done. 2.65 new questions per minute, 4.41 new answers per minute on StackOverflow, which to the mathematically inclined means that there's actually a lot more questions that are being answered right now. So there's a lot of results, a lot of raw data that's available to leverage from StackOverflow and similar sites, third-party blogs, and other resources that people might be using. There's also this notion of essential versus accidental complexity, and we argue that while deciphering how to accomplish getting your GPS location on Android is essential complexity, if you're doing it for the first time, there's no reason that you should already know how to do that. You're going to have to go through the struggle. But on the iOS side in Swift, why is that essential complexity? In reality, we argue it's accidental complexity. It just happens to be difficult because you're not learning anything from the Android side. And as we know, accidental complexity is one of the best candidates for automation. Quick market share. You can see the players: Android, iOS, Windows Phone, BlackBerry, others. There's the big players are Android and iOS. And this looks deceptive, like Android is the big market share, but this is just from the sales in 2013 and 2014, and there's a lot of devices that were being sold that had Android on it that weren't all from one company, right? They didn't all just come from Google or whatever else, Samsung phones and so forth. But you can see an increase. Mobile devices are entering the market at a very fast pace, and they're not slowing down. There's a lot of new devices, a lot of new operating systems. We can see there's 1.5 million apps on the Google Store, 1.4 on the Apple Store. Even Amazon has recently launched their phone with a marketplace. There's a lot of mobile applications available. Quickly, there's some translation methods. You guys are all familiar with traditional compilation. Everybody has done that at all points in time if you're sitting in this room. You've probably heard the term transpilation or source-to-source translation. which is something kind of like going from Java to C++, or maybe vice versa, or something of similar levels in languages. A very difficult task in itself, not very many good resources for that, and there's no way of universally accomplishing that for everything. There's things like Java to Objective-C by Google that translates Java, as you might have guessed, to Objective-C. However, it only does certain aspects of the code. It doesn't natively help you accomplish anything on Swift. It's really just the control flow of the algorithm, which honestly was the part that you knew how to do anyway. So we're going to introduce this concept of native translation, where we're going to try to natively generate this Swift code rather than trying to create a recursive parse tree or a method that tries to extract the semantics from the actual Android code block. There's two main components, right? We have to get the data. We have to use some sort of data mining techniques. We have to actually retrieve this information. We have to use it, analyze it somehow, have a metric for document similarity, rank them results, and then finally synthesize the code. Document similarity, just so we're all on the same page, this is just a formal methodology for comparing these two documents. This is crucial. If we can't compare them, we have no idea which one is more similar to the Android code block. A very high-level overview of what we've accomplished in this paper. We have a mobile developer. He has some input Android code. We have this fancy plugin. It does a whole bunch of things. And at the end of the day, it accesses web-based resources. All of a sudden, we have some Swift code generated that is hopefully very close to what you're trying to accomplish. There's three big things that we have to do in this approach. Kind of mention them at a high level. But we have to extract this core functionality from Android. We need to somehow extract the meaning of what we've done in the Android code block. Then we have to do searching and ranking. Lastly, the code synthesis, and somehow give the results to the user so that he can do something with it. Extracting core functionality really comes down to two kind of things. We have to tokenize and filter, and we have to run some frequency analysis. And these are not very fancy techniques. This is basic NLP. We are doing something similar to a bag of words model. We're really just taking the tokens and we're stripping them, we're filtering as best as we can, combining, concatenating certain things, using basic knowledge of programming, obviously making assumptions that may or may not be the case, but this is research. So we have to assume that the developer is competent enough to comment and name their variables at least somehow properly. And hopefully things like location variables are not called, Antuan's variable or something like that. But if that is the case, that's a very big bonus in our approach. And at the end of the day, we generate these query keywords, this set of keywords that we use to actually search for relevant documents. Searching and ranking consists of a couple of stages. First, we need to search all of these different, aspects, the web resources. We start with StackOverflow. We go straight to Google and ignore old StackOverflow posts that we've hit. We go to third-party blogs. We kind of scrape from Google searches. We have to be careful because too many searches and you get recorded as if you're a bot by the search engines and you don't want to get blocked. I got blocked plenty of times when I was doing the code for this. You learn how to be more efficient with your queries. Next, we have to convert this into a metadata object, which is just a middleman representation that allows us to compare the source Android code to all of the target documents in Swift that we find. And this is just a feature extraction in the tokens, which we'll go into detail in just a minute. Lastly, we then rank the results with this vector space model and linear model. I'm going to focus on the vector space model. The linear model you can see referenced in the paper for more details. So the vector space model is a feature vector per each document, and this is an n-dimensional vector where n is the total number of unique tokens across the entire document set of mined documents. So all of the Swift code we find, all of the Android code we had in the beginning, we combine all that together, we make one n-dimensional vector. And then it's just a zero if that token's not in the specific document, or this fancy W weight if it is. And the cosine between any two vectors is their degree of similarity. Very quickly, the cosine equation is just the dot product of each source, of the source to each target, divided by the normalizations of each. It's a really simple equation, and the weighting for each of the elements is determined by this, and this is just the normalization. But the weighting is determined by TF-IDF, term frequency, inverse document frequency, which allows us to prioritize certain tokens and make sure that others are ignored. Again, details on that in the paper for time purposes. Lastly, we get this fancy big equation, which looks like a giant mess, but is really just a combination of two models. It's just a maximum value of our linear model, which is independent of the source document, because it's just linear combinations, and a vector model, the vector space model, which is the source to each target. And that allows us to produce this overall ranking with this alpha and beta parameters. And now in a perfect world, if this was a longer project, alpha and beta would be fine-tuned, maybe with something like an SVM or some more advanced technique for actually fitting those parameters. But we just basically started with 50-50 and worked our way a little bit there, and ended up being 40-60 vector space model in favor for more accurate results. Lastly, this is useless unless we can give it back to the developer. So we have to generate a Swift file. We throw in the control flow as best we can with a very simple translation. And then we add the comment from the StackOverflow or Google or third-party blog, whatever we find. We generate as much of this as we can. It won't necessarily be syntactically correct, but it's going to get at least some progress, in a lot of cases, almost all of the way to what they wanted to accomplish in general in the first place. We insert this into the working directory, and they have this. A sample result. You can see some very simple control flow is translated. This is the actual GPS location result that we generated. So this is going to be, the comments that we saw in Java, a little bit translated. We have just the control flow for latitude and longitude. And we have this result, which happened to be from StackOverflow in this case, that you can see accesses the CL location manager. It sets some parameters. And what it essentially tells us is that this is not going to work out of the box, but this points the developer in the right direction and gets most of the job done for them. They don't have to go researching how this API works. They have an example, in most cases, right there given to them. So the APIs we used mainly consisted of ArrayList, HashMap, string, and then sensors. The sensors are the more important cases here. Those are the more practical. These are GPS, accelerometer, Wi-Fi, BTLE, sensors that you would leverage on a mobile device to try to accomplish some task. Our analysis was in kind of 4 categories. Understandably subjective, because we didn't exactly have a vast data set of iOS and Android code snippets that were identical or written for the same purpose that we could compare. So a lot of it we did have to write ourselves and kind of take a step back and look at it. So 4 categories, a strong yes, a strong no, 50-50, salvageable, or not a code block, which meant this had negligible utility. We're not interested in an explanation of how to do this. We want to synthesize the actual code. And you can see that actually most of the results were in the yes and no category. There was a lot of, it was very clear whether this accomplished something or didn't accomplish it. There's kind of no in between in most cases. This is just results for the top one answer. So we take the best ranked result, we give it to the user, and we go from there. 75%, 79% if we normalize each category. If we take the top 2 results, which is what we ended up doing, we get a nice little increase from there. Now we're up to 86%, 85% normalized for how much of this code block actually does almost the entire job for us. So there's a couple of issues. iOS is a closed source platform. This is a problem. Swift is actually being open sourced in the coming months, I believe. In the next major release it should be, which is going to help with this a lot. But in general, it's very difficult to find something that implements 2 logical pieces on both sides. So we took what we could find, and then we wrote additional components from previous projects for GPS getting and accelerometer data, things that we had written on one or written on the other, and we compared them, and we looked at APIs, and we saw, well, what was being leveraged? What did we need? What would we have liked to do if we were a developer writing this from scratch? We had to use things like reflection to generate some of the Java test cases to help us speed things along. Otherwise, this process was never going to get done with enough test cases. We also had things like vocab discrepancies, which were very minor, thankfully. And this is the major case that stood out. Well, there's no notion of a hash map in Swift. It's called a dictionary. So if you search for hash map things in Swift, you get things like the MD5 hashing algorithm, which is actually not what we're interested in. So this was, a very clear-cut no result. And this is quickly resolved by having just a static mapping of a couple of keywords that are off. The biggest one that made a huge difference was just telling the system, by the way, a hash map in Java or variations thereof are actually a dictionary or a dict and things like that in Swift. A couple of future works that we wanted to discuss. There's really this big one of a preference server. Anytime you do anything with this kind of system where you are storing information or a user is repeatedly doing a system, you want to incorporate a preference server. Unfortunately, we didn't have enough time for just this paper, but this is one of the bigger things on the table in terms of how we would improve. And this is something that you could easily get better results with, simply because, at least for myself, when I'm doing something in Java, I never remember how to read in and out of from standard in. I go to the same Stack Overflow post probably 3 or 4 times a month in some cases. A lot of people are very similar who are constantly developing certain things. They're going back to the same posts. A lot of times, this could be fine-tuned so that you could just auto-generate a lot of the simple algorithms for you that you're constantly doing for ideal little logical bits. You also have things like Swift to Java, the reverse direction. This is actually what we're doing right now for the actual close extension of this paper. And this could incorporate things like Windows Phone. There's also a phone gap, which is one of our related works that we mentioned. Things like that go for just spreading the wealth, so to speak, going to more platforms. The heterogeneous nature that we talked about at the beginning is very important. We want to go to different platforms. We don't want to just stick on Android and iOS, and definitely not just on Android to iOS. Going in the other direction is actually not that difficult either, because Java is very long and takes a lot of time to say certain things, and Swift is a lot more concise. So going Java to Swift was actually a little more difficult. The reverse is everything you have in Swift is typically important. So here's kind of this one-line conclusion, right? So what do? We presented this approach for automated code synthesis. We took web-based programming resources and we combined them and generated and synthesized this iOS code file or Swift code file that we gave back to the user that, given some Android code block, it tries to figure out what it means and accomplish as close to that as possible for the user in Swift. And the main takeaway here is that even if this does almost nothing of value, but it hits the right APIs, at least it's taking the user into the right direction. So there's always some value from doing something like this because you want to extend your platforms. You want to have at least Android and iOS if you're writing a mobile application. Availability. The source code is available on this GitHub page over here. It's completely open source. We encourage you to use it as an application or contribute if you have anybody wants to have other features added or fine-tuned, by all means. There's also some additional results and more use cases and things like that are available. Quick thank you to the anonymous reviewers, also a couple of extra guys that were very helpful during the review process from our teams and colleagues in general. But related works, the big related works that we wanted to hit, these are referenced in the paper. If you have any questions about these, see me after, or by all means, feel free to message me about that. All right. Thank you guys. Any questions?